right. Questions?
When's your birthday?
September. It's always like the first week of school, which is kind of a drag. Except like you had lots of friends there, so you get like gifts and stuff. All right. I want to talk about the file class briefly. So java.io.file. We can use scanner to read from system.in. If you want to read from a file, which you don't need to do for PA3, this is not a hint for PA3, but in general, if you want to read from a file, you can still use the scanner class, but instead of constructing scanner with an argument of system.in, you can construct it with an argument of type file, which is an object you can construct from a path name. So let's play with this. So I'm just going to say file f equals new file, and I'll just call my file haha. And it doesn't know what file is because I didn't do my import, so import java.io.file. And it doesn't do anything. I don't have a haha, oh, look at all that stuff. Ignore all this. All right, so I don't have a haha inside here, but I can construct a file off of this string haha, and that works perfectly fine. So what can we do with files? We can say something like, can we execute the file? Can we read the file? We can compare a file. We can delete a file. We can ask whether the file exists. We can convert into an absolute path name, etc., etc., etc. So let's play with this. So let's see what f.exist says. Alright, so f.exist is false because I don't have a file named haha. If I make a file called haha, right now f.exist returns true. So you can do various tests on your file. You can delete the file. We can also say list. So list is a method that returns an array of strings, naming the files and directories in the directory denoted by this abstract path name. So let's try that. So I'm going to say directory info equals f.list. And f.list should be an array of strings. So instead of doing this on haha, let's do this on my parent directory. So dir info has to be an array. And so if I try to print out dir info, it's an array, right? It's not going to show me the elements of it. It's just giving me this weird internal, because there's no built-in toString method for that. But how do we print out the elements of an array? Yeah, we'll just make a loop. So how many elements are in this array? Not necessarily. Yeah, dot length. And remember, there's no parentheses. We're not calling a method here. We're just grabbing a field. So there's just a basic for loop. And we'll just print out each element from the dir info array. And there's a directory program. So that shows me everything that's in this case in my parent directory. And it's not strictly alphabetized. In fact, there's no particular rhyme or reason apparently to the ordering of these. But there's no claim that there is. There's no guarantee that the name strings in the resulting array will appear in any specific order. They are not in general guaranteed to appear in alphabetical order. But it gives you a list of names. Now we could alphabetize it by various methods.
So when you call ls, does ls alphabetize them?
Mm-hmm. Yeah, and that seems to be a alphabetizing that's ignoring the order, the uppercase, lowercase. Alright, so a little setup comes before a big S, comes before a little t. But that's just what the code in ls is doing. So file is a really powerful class. Right, we can use it to interrogate directories. We can ask it, for example, is the file itself a directory? So we could do something like this. If element I of our directory info let's make this a little fancier. Dir info bracket I is a string. Let's make a file out of that. So we'll say new file of that string, and that file should have an isDirectory method. And we can call that, and if that returns true, we'll print out a message that says is a directory. That didn't work. Just imagine that it worked. Oh, thank you. Thank you, because it's coming from the parent directory. So check out that file. Cool. So s.class is not a directory, Spring 2016 is a directory, and so on. So if you wanted to make something that would show you every file on your system, would that be hard to do? Would it be a good place to use recursion? Right? Just make something which displays everything from some directory on down. And to do that, open up as a file, use the lists method, go through each thing that lists returns in the array, and if the result is a directory, recursively call yourself on that directory. You got to put in, you know, the prefix for the path name and stuff, and it should just recursively go down the whole tree.
Wouldn't you have to open each file though? And when I've been messing around with it, usually there's like a 1024 limit of how many files can be opened.
Is there?
At any one time.
So first of all, we're not opening the file.
Oh yeah, I get you.
Right, because we can construct a file object even on something that doesn't exist. Is there really a 1024 limit on how many files you can have open?
I had a leak in a program a while ago, and it was basically opening files and not closing them, and then it crashed and said like, you've gone over the max file open limit.
Oh, cool. I definitely believe that in C. I never tried it in Java. That's interesting. But yeah, so to do this, we don't have to actually open the file. So that shouldn't be an issue. But if you have a link pointing to a parent directory, you could get yourself in an infinite loop, depending on how you deal with links. But so doing some kind of like recursive file traversal is not a big deal. You can also just use the find command. It does the same thing. You can say find path, and it'll find everything from that path on down. All right, so for us, if we want to read from a file, we need to construct a scanner off of it. So exactly what we would do to input line by line from standard in, but instead of constructing the scanner on system.in, we construct it on this file F. And this should work fine, but when we try to compile it, it's going to tell us that this scanner construction might throw an exception. Now, if we construct on system.in, we can't get an exception. But if, for example, the file associated with F, doesn't exist, this will throw an exception. So we got to put it in the try-catch block. And usually you want your try-catch blocks to be as small as possible. And I'm just going to catch all exceptions. So we'll try to open the scanner. If we get an exception, we'll go to the catch block. We'll say we couldn't open the file, and we'll print out what the string value of that exception is, which will probably be file not found. and we'll say return. This is not going to compile yet. And this happens almost all the time when you put try-catch blocks around things. It no longer has access to this object SC because SC is declared inside this try block, so it's local. So quick fix for that, just declare your scanner outside of that block. So compile it up and run it. And haha is an empty file, so it didn't show me anything. If we remove haha and we run this, then we jump into our catch block, which says couldn't open file, and it shows us the exception message. Alright, so if you have stuff in the file, it'll show you the contents of the file. If you don't have permission to access the file, you'll get a different kind of exception, saying permission denied, and so on and so forth. Make sense? So that's a way to do input from a file. You can always read from system.in, right, standard in, and just redirect with a less than sign. But if you want to open a file and pull information inside, you can use it with a scanner. And scanner is good enough for most of what we're ever going to have to do in this course for doing input. All right, what about the output side? What if you want to output to a file? So there's a class called PrintWriter, java.io.printvwriter. You can construct it with a file, okay, or you can construct it directly with a file name. And it has a series of methods including print and printline. In fact, the same methods that we have available when we say system.out. We can use with a PrintWriter. But instead of printing to standard out, it'll print into a file. So let's import our PrintWriter class. Java.io PrintWriter. So I'll just call this PW. And I'll just call this myfile.txt. And instead of systemout.println, I'll just say printwriter.println. And so this should open the file haha and read in the input and then copy it into a file called myfile.txt, which doesn't exist right now. And again, this has got to go in a try-catch block. So PW is a PrintWriter. We'll try to set PW equal to new PrintWriter. We'll catch an exception saying we couldn't open the output file, and we'll just return. So compile that, run that, no errors. There's a myfile.txt with nothing in it. Even though haha has stuff. So PrintWriter has a method called close. And closing will, among other things, flush your output buffer. I thought it would have flushed automatically. So it's called the close method. Alright, so there's your output. So just like everything else we've done in a Unix environment, when you do output to a file, for example, the file may not actually get anything in it until you close the file, because all of our output is usually buffered. So we say print this, print that, print this other thing. It's going into a holding bin, and the intent is that when you have enough stuff to print into the file, it gets pushed in all at once. It's more efficient than writing a character at a time or a line at a time. But if you don't call the close method, the contents of that holding area may not get dumped out to your file. So you definitely need to close PrintWriters and other output systems. All right, any questions on PrintWriter? And PrintWriter and Scanner are probably enough to do most of the basic output and input that you're going to need to do. Certainly for PA4, that'll suffice, and probably for PA5. But there's whole sections of the Java documentation on input and output, and there's different versions of input and output. There's buffered versus unbuffered. And we may get into some of that later. But to get on the air with I/O, Scanner for input, PrintWriter for output is sufficient. I don't have a network. I'll copy those over later. No questions? Everybody see the new quizzes? Okay, cool. All right, so let's talk about a linked list class. So we know how to write linked lists, and we can do them ourselves, and on tests we'll probably do them ourselves. But there's already classes available for us in Java for implementing linked lists. And it's just called linked list, comes under Java utility. And they're pretty straightforward to use. So constructor is just linked list, no arguments. You can initialize it with a collection of things, but if you just want an empty linked list, it's just new linked list. And then there's a series of methods. So we can say add, which puts an element on the end of the linked list. We can say add an element at a particular position, an index, which is kind of what we would do with an array, right? Array bracket I equals x. Well, we could say array.add I comma x. And it will put it in that, ith position in the linked list. If we already have what's called a collection, right, of objects, we can put them all together on the end. We can add something to the beginning of the list, and we can explicitly add to the end. We can delete everything from the list. We can make a copy of the list. We can see if the list contains a particular object, right? These are all the kinds of things that we coded up manually in, say, 222. And they're all available for us. We can retrieve an element by its indexed position. We can get the first or last element. We can search to see if an element is contained in the list and find the index of it. And we'll talk about iterators in a moment. We can look at the first element without removing it. We can look at the last without removing it, and so on and so forth. We can push and pop, and if we want to treat this linked list like a stack. We can find how many elements we have, and we can convert the whole linked list into an array. So this has, the capabilities of the lists that we were putting together in 222, plus a lot of other stuff. So let's play with this. So let's make a linked list. And let's just add some things to the list. Add 5 numbers to our list, and then let's see what our list looks like. Straightforward. I forgot my semicolon. Alright, so I can compile it up, and we'll talk about this warning message later. This is a warning using unsafe operations, but let's just go ahead and run this anyway. So we'll run ll-demo, and when we concatenated the linked list to our string, it turned it into a comma-separated list of node values inside square brackets, which is kind of cool. So it works like a linked list that we're used to. Okay, so let's talk about this note when we did our compilation. It said ll-demo Java uses unchecked or unsafe operations, recompile with -xlint, unchecked for details. So lint is about cleaning up little details. When you compile a C program, you can run it through something called lint, and it will tell you about things that are not errors and not quite to the level of warnings, but that it still notices as being odd. Okay? Java by default, when we say Java C to compile something, it suppresses certain error messages. If we want to see all of those details, we can say something like Java C dash xlint, and the name of the file we want to compile, and it will give us some more information. So we got 7 warnings here, starting with raw types found raw type linked list, missing type argument for generic class linked list angle bracket E, where E is a type variable. E extends object declared in class list. So this goes on and on, right? We got 38 lines of error messages there. But it's all basically telling us the same thing. So there's a notion in Java that I mentioned a few weeks ago called a generic, right? And the idea of a generic is certain things that we write, certain classes, like a linked list class, the code is almost exactly the same whether we're making a linked list of integers or doubles or strings or rectangles or fractions, right? The linked list operations are pretty much identical. The only thing that changes in our code is somewhere over here we said int, and now we have to say double, or we have to say string. And so rather than making a bunch of classes, integer linked list, double linked list, string linked list, we can customize this one class called linked list to work with different types of objects, including things like rectangles or fractions or calculators or word lists or any other kind of object. So the syntax for doing that is to, after you say linked list, angle brackets, put in the name of the class that you're planning to make a linked list of. So that will specify a linked list of integers. And it compiles without any kind of warning. But now, if we want to make a linked list of strings, all we got to do is that. Instead of linked list, it's linked list of type string, ll equals new linked list of type string. And now on these adds, so now we can say ll.add and we can put strings in. And there's your linked list. And if I try to add an integer to that, right, it's going to warn me that that's not an appropriate type of object. Right, there's nothing in my LL object for adding an integer. There's only things for adding a string, because that's what I constructed it with.
What if you did 5 and then concatenated it with a string? Did that?
That should be fine, because now when you concatenate something to a string, it calls the toString method in that something, the 5 in this case, that'll turn it into a string 5. And so that should be calling the add method with just a plain old string.
Is it possible to access just certain locations within the? Okay. How would you go about that?
So there's a get method which returns the element at a specific position in the list. So we could do something like this. So how many elements are there in the list? There's a size method, returns the number of elements in the list. So for I equals 0, I less than linked list dot size. And then let's get element I. Well, that's just a get method. So we can say get and give it an integer index, and it'll return an object. It's saying E here, right? E is the thing that we used when we constructed the list. So type parameter is E, the type of elements held in this collection. So anytime that's going to return an E, it's whatever you constructed with strings, ints, rectangles, etc. So let's do ll.get I. And we'll just print those out in a loop. Is that what you were asking? So this is a really powerful class. Right, it takes almost no work to build a list, takes almost no work to work with the list.
That's why we don't need another class contain the add.
Say again?
So we don't need another class to contain the add function like just.
No, it's part of the linked list class.
We don't need another class like the add node.
No.
Oh.
Yeah, so the way this is implemented is hidden from us. Right, this might be making a linked list. Remember, you can make a linked list with just a plain old array. And you can insert something in between two things in an array by moving everything down. Maybe that's what's going on inside the linked list class. We have no way of knowing. Right, or maybe it really is a linked list. Maybe it's a doubly linked list. Maybe it's a circular doubly linked list. Maybe it's magic. It's completely hidden from view, right, and it doesn't affect the way that we use it. Because this is all we see is these ways of interacting with this structure. So clone is an interesting method. So return a shallow copy of this linked list. The elements themselves are not cloned. So if I have a linked list of integers and I make a clone of it, here's the idea. There's the original. The clone looks like this. If I go into the clone and I say delete 6, right, my clone looks like this, my original still looks like that. So I have a new linked list down here which has the same stuff my original list had, but it's an independent entity. Now if I were to do something like clone equals original, and I delete 6 from the clone, that's also going to delete 6 from the original because they're exactly the same object. But if I say clone equals original.clone, right, it's a new linked list that happens to have the same values in its nodes as the original, but it's an independent list. But it's what's called a shallow copy. And here's what a shallow copy means. So here's my original. Suppose I have a linked list of rectangles. So here's rectangle 1, and here's rectangle 5, and here's rectangle 2. And let's say this is a 1 by 1, and this is a 2 by 3, and this is a 4 by 7. And I clone this. I have a new linked list, but the objects themselves are exactly the same objects. If I delete R5 from this list down here, I haven't disturbed the original list. But if I go in and I change R5 to be an 8 by 8 rectangle, this also becomes an 8 by 8 rectangle. So it's making a copy of the list, but the elements of the list are the same as the elements in the original. For primitives like int or double, that makes no difference. But for objects, we've actually got two things that are pointing to the same object, and those are linked together. If you really want a totally independent copy, you have to do what's called a deep copy. And deep copying is often something you have to do yourself. In other words, I would make a new list here, but I would take this and I'd replace it with a copy of R1, which means make a new rectangle with the same dimensions and whatever other fields a rectangle has associated with it. And this probably won't come up in this course, but it's guaranteed to come up in other courses, this idea of deep copy versus shallow copy. And it's a really kind of annoying bug to try to track down, because your code looks like it's working great, and now you do something in some piece of code over here, and all of a sudden this stuff that was working great breaks, right? And it's because you're perturbing other areas of memory when you do something that seems harmless down here. So it's something to keep in mind, and you'll see it in other courses. Probably won't come up for us, but maybe I'll do an exercise with a linked list of rectangles to flesh this out. You look concerned.
Why would you bother making a shallow copy then instead of just passing the pointer to the original?
Because if you pass a pointer to the original, I destroyed my list. If I say something like clone equals original, I only have one list.
But if you change one, then it changes the other.
But if I actually make a clone, say I use the clone method, I can manipulate this list. Right, if I actually make a clone, I can manipulate this list, not the contents of the nodes, but I could, for example, delete this, and I could insert something new after here, and it doesn't change the original list. Okay, but the contents of the nodes, if they're the same objects, right, then they're tied together. So if you just say clone equals original, you get an exact, you're pointing to the same object from two different things. If you say original.clone, shallow copy, then you've got an independent list, but the nodes themselves are the same objects. And if you do a deep copy, then you've got completely independent things. But doing a deep copy automatically is kind of tricky because you have to understand, this is a rectangle, which means I have to make a new rectangle and I have to set the height and the width, and maybe it's got a word list inside. And so I have to make a copy of the word list, which means a new linked list of words, and each of those has a location list, which has to be a copy of the location list, and so on.
So, is there a reason that you can't just say like new linked list and then just traverse it, and as you're traversing it, set your new field?
Yeah, that would be a good way to get a deep copy.
Okay.
Yep. Alright, so that's part of the deal with cloning. You could also turn it into an array and then turn the array into a linked list. Copy the individual elements. Alright, well, when we did linked lists by hand, we wanted a way to traverse them, to go through and display the contents of them. And we've already done that here, right? One way, if we just want to display, is to use a toString method. But that's got a very particular format that may not be suitable to us. Another way is to make a loop and use the get method and get each element one by one. And that works because when you have a linked list, there's a way to associate each element with some particular location. We can say this is element 0 in the beginning, and then element 1 and element 2. We can assign an index. So for a linked list, getting all of the objects from the list is pretty easy to do with a for loop. For other types of data structures, there may not be a natural ordering. For example, when we look at hash tables, there's no inherent first element to a hash table, or second element, or third element. Right? If you implement it with an array, we could say what's the first element in the array, but maybe your hash table isn't implemented with an array. Maybe it's implemented with magic, right? So a lot of these structures we're going to work with, there's no such thing as a first element. And so we can't use something like a get method to do something like, object.get I from 0 up through the number of elements. So there's a general construct for traversing these data structures, for getting things out of your data structures, and that's called an iterator. Let me go back to the index here. So if we have a linked list object, know what I'm looking for. This is not a really good example. Alright, this is not a good example to work with, so let me tell you the general idea of an iterator, but we'll dig into the code with hash tables. So you have an object, right? Most of these objects come with a method for getting what's called a list iterator, or an iterator in general. An iterator is something like a scanner, in that you get this iterator and it has a series of methods like hasNext and next. So get yourself an iterator, and then you can make a loop that says, while this iterator has a next entry, get the next entry and do whatever you want with it. And every time that you call next, it will give you another object from your structure. And in no particular order, right, but without repeats, it will go through until it's given you every single item inside your structure, at which point if you say hasNext, it'll come back false. So that's the basic setup. We'll play with code for it when we get to hashes and hash maps later this week. Because it doesn't make a lot of sense with lists, because for lists they actually want you to give it an index, and the whole idea of an iterator is you don't need to have an index. But we'll play with that. Alright, if anybody did not sign in on your way out. And we will dig further into some of these structures tomorrow.